welcome to Lecture 7, Chapter 3. In the previous chapter, I described briefly some of the key elements of the methodology we adopted in the Deep Decarbonization Pathways project. In this chapter, we're going to look at some of the results now. So what do we learn from the analysis of the 15 research teams of their respective countries' pathways to deep decarbonization? Well, first and very importantly, so let me pause a moment on that. Their results show that deep decarbonization is feasible. It's a very important result. It shows that we can avoid dangerous climate change if we take strong and early action to reduce greenhouse gases emissions, if we invest heavily and rapidly also into some of the key pre-commercial low-carbon technologies that are critical to achieve deep decarbonization at relatively low cost, and also if we more profoundly reorient our development trajectory. I must say that the DDPP is still at an early stage. We have much more research and analysis, and I hope good results coming in the upcoming months or even years. So far, the country research teams have only produced a first set of interim results. So the precise level of emission reductions that is reached by the different pathways and that I'm going to show you is in many ways less meaningful than simply their order of magnitude. So that's what I want you to concentrate on. The order of magnitude of emission reductions achieved by these pathways is very substantial. As you can see on this graph, it represents an absolute decrease of emissions by 45% in 2050 compared to the level of emissions in the same 15 countries in 2010. As you can see on this other graph, it also represents a 56% decrease in emissions per capita and even an 88%, so very close to 90% decrease in emissions per unit of GDP. So the CO2 energy-related emissions divided by the GDP in 2050 compared to the level in 2010. Let's look more closely at some of the results sector by sector. The results also show the pivotal role played by electricity in the deep decarbonization strategies of all 15 countries. In aggregate, across the 15 countries, the carbon intensity of electricity, so the ratio in between the CO2 emissions and the electricity generated, measured in kilowatt hour, is reduced by a stunning 94% in 2050 compared to 2010. So that's a huge number. It means that by 2050, really electricity is almost completely decarbonized in these 15 countries taken together. As you can see on the graph, the carbon intensity of power generation goes from a bit more than 600 grams of CO2 per kilowatt hour in 2010 to approximately 30 grams of CO2 per kilowatt hour in 2050. So it's really, really a huge drop. And it means, as I said, that essentially electricity is almost zero carbon by 2050. That's why electricity plays such a pivotal role in the deep decarbonization strategy, but it's not the only one. There is another explanation, and it's because in the meantime, electricity plays an increasing role in the energy system. A higher share of the electricity consumption is met through electricity as opposed to other energy carriers. As you can see on the graph, the share of electricity in final energy consumption increases from 19% to 35% in 2050 compared to 2010. But that was for the results in aggregate, so making averages across countries or looking at the total out of the 15 countries. But what is especially interesting is that the results also show the different options that are available to the different countries, in particular to reach that common goal of the deep decarbonization of power generation, electricity supply. It's true that by 2050, all countries generate electricity almost exclusively through zero or very low carbon energy sources, but they rely on very different options, to be frank, to do this, as you can see on this graph. So let me just pick a few examples. Australia, Mexico, South Africa, and South Korea, for example, rely heavily on solar energy as part of their power mix. It can be different types, by the way, of solar energy. It can be solar photovoltaic, or it can be concentrated solar power. It can be centralized solar energy or decentralized solar energy. But all of these countries have a very high share of their electricity that is coming from solar energy by 2050 in the pathways developed by the research teams. Wind power plays a very important role in Canada, in China, in France, in Germany, in India, in Japan, and also in the United States, where there is a significant potential for wind power that can be tapped into. Hydropower plays a very important role in Brazil and Canada, also because there are large and sometimes still untapped resources of hydropower in these countries. Nuclear, on the other hand, represents a significant fraction of power production in many countries: France, the UK, China, India, the US, and Russia. It plays a very little role, but still a role in some other countries such as Brazil, Canada, Indonesia, Mexico, and South Africa. And CCS, very importantly, also plays a role in some of these scenarios. Remember, as we have discussed in the previous lecture, CCS is not yet deployed at scale, even though each and every element of the technology is a proven technology. But in the project, we've made the assumption that as a result of a strong and sustained effort on research and development, CCS could become available. And in fact, many of the countries in the project with high shares of fossil fuels, so coal or gas, in their power generation today felt like it was an important element of their decarbonization strategy going forward. So you find carbon capture and sequestration in the scenarios that were developed by Canada, by China, by Indonesia, by Japan, by Mexico, by Russia, or the UK and the US. I want to mention here that these pathways and their results are, of course, only illustrative. I mean, they shouldn't be confused with the precise reality of what is going to happen in these countries, or even what should happen in these countries, because there are many different ways in which the deep decarbonization of power generation in particular can be achieved at the national level. For example, in the project, the team producing the pathway for the US developed not just one, but three different pathways, with, in the different pathways, higher shares of renewable energies for one, or nuclear for the other, or fossil fuels with CCS for the third pathway. And it's very important to recognize that the most effective but also cost-efficient way of achieving deep decarbonization is of course subject to debates. First, within the expert community, we had disagreements first. We tried to settle in the project, but it should also, of course, be the topic not only for an expert discussion, but it should become the basis for a political debate within each country and each society. So for sure, there are different options, different trajectories to deep decarbonization in the future. But it is absolutely critical that these debates happen on the basis of detailed roadmaps for the deep decarbonization of the power sector, but also of the economy more broadly. These detailed roadmaps need to be based on transparent assumptions regarding the availability of some pre-commercial technologies. They need to be based on transparent assumptions regarding the projected cost of these technologies. Also, transparent assumptions regarding their resource requirements. I mean, how much water do we need to use, or how much land do we need to use to operate these technologies? And also transparent assumptions regarding their possible side environmental and health impacts. There are really important choices to be made regarding the best options for deep decarbonization based on considerations regarding economic competitiveness, energy security, or public preferences. But these choices need to be made within the constraints of a global carbon budget to stay within 2 degrees of global warming. The result of the pathway analysis also reveals in which sectors the emission reductions are relatively, at least, most difficult to achieve. Because in total, if the 15 pathways achieve an absolute reduction of CO2 energy emissions, the share of the emissions of some sectors, and in particular the share of emissions from transport and industry, is increasing in the pathways taken collectively. The analysis reveals that within the transport sector, it is the emissions from freight as opposed to passenger transport, which are, again, relatively more difficult to decarbonize. As we have discussed, there are lots of different technological options to achieve the deep decarbonization of the freight and heavy industry sectors, natural gas, electric hybrid and hydrogen fuel cells powered trucks, biofuels or synthesized fuels for air and ocean shipping, electrification of heating processes, but also carbon capture and sequestration maybe for industry. But it's true that the feasibility and the scalability of these options is sometimes still uncertain, and their costs are also likely to be quite high. And this is why some of the teams in some countries found it difficult to build in these technologies in their decarbonization model. So to conclude this chapter, the pathway analysis that was developed by each of the country research teams, and although they're only at an interim phase at this stage, they already provide lots of very interesting insights on the country-specific challenges of deep decarbonization, but also, and most importantly, the possible solutions to them. We will revise the analysis in the coming months. We will for sure explore the potential for even deeper emission reductions, because we're not completely there yet. We will test the robustness of the analysis, add some new dimensions such as infrastructure stocks, an analysis of the costs and benefits, an analysis of the policy frameworks to support the implementation of these different actions. But really, you should also try to think about it yourself. You should try to come up with alternatives to what we developed, and who knows, maybe you would come up with even better solutions.